Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 asks, how many moles of N2 gas occupies 5.2 liters at negative 23 degrees Celsius and 0.5 atm? Okay, so to answer this question, we are going to assume that the diatomic nitrogen gas acts as an ideal gas. So the reason we want to assume that the N2 gas acts as an ideal gas is so that we can use the following equation where PV is equal to nRT. So the P stands for pressure. And in our case, the pressure was given in the question, so it was 0.5 atm. The volume is V. And they gave it to us, it was 5.20 liters. And we're trying to find number of moles, so we're going to leave that. But the R is known as the ideal gas constant. So depending on the units, R can have different values. But for this question, we're going to use the value 0.0821. And the reason why is because its units are in liters times atm divided by mole times Kelvin. So since our volume is in liters and our pressure is in atm, then we can use this ideal constant. And now T is temperature. And they gave it to us in the question as negative 23 degrees Celsius. But we need to convert this to Kelvin in order to use our ideal gas constant. So to convert to Kelvin, we just need to add 273 and you end up getting 250 Kelvin. Okay, so now let's try to sub in all our values and rearrange this equation so that we solve for the number of moles. So if we rearrange this equation, we get number of moles is equal to PV over RT. The P was pressure. V was volume. R and finally temperature. Okay, so now if we want to cancel out all our units, you'll see that our ATM will cancel out, and our liters, and our Kelvin, and now our moles will go from the denominator to the numerator. Well, it'll be our final units, and you get number of moles equal to 0.127 moles. Okay, so let's see what the junior tutor said. They summarized all the different variables in the ideal gas equation, rearranged it, plugged in all of the values, and also got 0.127 moles of nitrogen gas. Okay, so this solution is correct. Okay, so question number 2. What is responsible for the difference in intermolecular forces exhibited by polar covalent and nonpolar covalent molecules? Okay. So for nonpolar covalent molecules, they only exhibit something known as London dispersion forces. And what London dispersion forces are is they are the weakest intermolecular force, and they are the temporary attraction or temporary attractive force that results when the electrons in two adjacent atoms form temporary dipoles. Okay, so these are London dispersion forces. And we can also compare all the different intermolecular forces exhibited by polar covalent molecules. Okay, so polar covalent molecules also exhibit London dispersion forces. And they can also exhibit something called dipole-dipole interactions. So a more specific dipole-dipole interaction would be something called hydrogen bonding. So hydrogen bonding isn't just hydrogen covalently bonded to another atom, it's a bit more complex than that. So let's say we had a water molecule, and we know that the oxygen is much more electronegative than these two hydrogens. And because of the bent structure of water, we don't have anything canceling out this dipole moment. So we have a net dipole moment pointing towards the direction of oxygen. And because of that, the molecule now has a partially negative and partially positive sides to it. So now, if we have another water molecule that's close by, it also has partially positive and partially negative ends. And because of this partially negative side from one molecule is attracted to the partially positive side of the other molecule. So this is known as hydrogen bonding. So in order for hydrogen bonding interactions to take place, we need a hydrogen being connected to an electronegative atom, such as oxygen or fluorine. And because of this, it creates that partially positive, partially negative side. And we also need another molecule of hydrogen being bonded with another electronegative atom for those two sides to be attracted to each other. Okay, so let's see what the junior tutor said. Nonpolar covalent molecules can only experience London dispersion forces, while polar covalent molecules can experience other types of intermolecular forces, like the dipole-dipole forces, or its special form, the hydrogen bond. Polar covalent molecules are capable of experiencing these because these molecules have dipole moments, which are these charged regions. They can attract the oppositely charged regions of other molecules. Okay, so this is correct. Okay, so question number 3. Ammonia is a weak base with a Kb value of 1.8 times 10 to the negative 5. Calculate the initial molar concentration of a solution of ammonia if the pH is 10.06. Okay, so first let's write out the reaction between ammonia and water. So the ammonia is a base, so it will accept one of the protons from water and become NH4+, which is the ammonium ion. And then our water just lost a proton, so now it becomes OH-. So now we can construct an ice table for this reaction. So we are trying to solve for Y, which is the initial molar concentration of a solution of ammonia. So I'm just going to denote this as Y, because for the change, I will denote this as X. So at equilibrium, the concentration of ammonia is Y minus X. We don't need to focus on water since it isn't really part of the reaction here. And for NH4+, it has an initial concentration of 0. And the same thing with the hydroxide ion. They both start off as 0. And for the change in concentration, going to be positive X. And now at equilibrium, their concentrations are equal to X. And we were also given the Kb of this reaction. So Kb is equal to 1.8 times 10 to the negative 5. Okay, so now let's write out an expression for Kb. So Kb is equal to the concentration of our products, so NH4 plus times OH minus divided by the concentration of our reactant, which was NH3, and these are all at equilibrium. So you can see that we have like a bunch of unknowns. Well, we have two unknowns. We have Y and X. But this question also gave us pH. So pH is equal to 10.06. So if we recall that POH is equal to 14 minus pH, then we can solve for the POH of this solution. So 14 minus 10.06 is equal to 3.94. And now that we have the POH, then we can actually calculate the concentration of our OH minus ion, because this is the same thing as 10 to the power of negative POH. So now we just sub in our POH value, so negative 3.94, to give us a concentration of 1.148 times 10 to the negative 4 moles per liter. So let me show our Kb expression if we were to sub in all of the variables. Notice that for both NH4 plus and OH minus, they're both X, so we can rewrite this as X squared. And for our denominator, concentration of NH3 at equilibrium is Y minus X. But now, since we know the concentration of OH minus, this is the same thing as our X value, so we can just sub that in to our equation. So 1.148 times 10 to the negative 4 squared divided by Y minus 1.148 times 10 to the negative 4. And also, I can even write in my Kb as 1.8 times 10 to the negative 5. So now I only have my one unknown, which is Y. So let's just try to isolate and solve for the Y. And when you do the following calculation, you should end up with 8.47 times 10 to the negative 4. So therefore, the concentration of NH3, well, the initial concentration, is equal to 8.47 times 10 to the negative 4 moles per liter. Okay, so now let's see what the junior tutor said. So first they got the pOH, they got it 3.94, and then they found the concentration of OH minus, 10 to the power of negative 3.94, and they got 1.148 times 10 to the negative 4. Then they showed their ice table and the Kb expression, and then subbed in all of their known values. And when they solved for y, they also got 8.47 times 10 to the negative 4. So this solution is correct. Okay, so question number 4. Ammonium chloride reacts with barium hydroxide in an aqueous solution. Part A is to write the total ionic equation, and B is to write out the net ionic equation and list the spectator ions. Okay, so before we write the total ionic equation, let's first write out our molecular equation. So we have aluminum chloride. So aluminum has a 3+ oxidation state. So that means we need 3 chlorine atoms to neutralize the aluminum so that we have a neutral compound. So this reacts with barium hydroxide. So barium has an oxidation state of 2+, and hydroxide has a charge of -1. So we need 2 hydroxides to neutralize our barium 2+. And if a double displacement reaction occurs, so let me just make some space. To write in all the states. Okay, so when a double displacement reaction occurs, then our aluminum will now be paired up with our hydroxide. So now we have aluminum OH3, and we don't know what state it's in yet. And the same thing with our barium hydroxide. So it becomes now barium chloride, sorry. And again, I'm just going to put its state in brackets. Okay, so to find out whether or not these products are aqueous or if they precipitate, we need to look up the solubility rules. Okay, so let's try to find a good chart that summarizes all the different solubility rules. So when we have a compound that contains lithium, sodium, potassium, or ammonium, these are always going to be soluble. The same thing with a nitrate or this ion, it's always going to be soluble. And let's try to find one for our example, such as the OH minus. So hydroxide is soluble with calcium, strontium, barium, lithium, nitrogen, potassium, and ammonium, and it's insoluble with any other ion. So in the case of our product, it is with aluminum. So now we know that this compound will be a solid and precipitate in solution, since aluminum isn't part of that list. And now let's look at the barium chloride. When we have chlorine, bromine, or iodine, then this is insoluble with silver, mercury, and lead, and soluble with any other ion. So since we have barium, then this will be soluble. So it's going to be aqueous. Okay, so we have all of our different compounds in the molecular equation, and now we just need to balance out this equation. So notice that we have 2 hydroxides on our reactant side and 3 hydroxides on our product side. So I'm just going to take those subscripts and make them the coefficient on the opposite compound, just so that they both now have 6 on each side. So this affected the number of barium atoms. So now I have 3 bariums on one side. So now I'm just going to put a 3 in front of this barium. So now we have 6 chlorines and 2 aluminums. So to fix that, all we need to do is put a 2 in front of aluminum chloride. And now we have our balanced molecular equation. Okay, so now that we have our balanced equation, we can start with part A to write out the total ionic equation. So ionic equation. And when we write out ionic equations, we basically separate all these compounds into their respective ions as long as they're aqueous. So if we had a solid or if we had a pure liquid, then these do not separate into their ions. So let's separate aluminum chloride. So this can be 2 aluminum 3+. And we have a coefficient of 2 and a subscript of 3 for the chlorine. So in total, we have 6 Cl- ions. We have 3 barium 2+. And we have 6 hydroxide. So these are just all of our reactants. So I'm just going to write our products on the second line. So our precipitate stays the same. It's the only one that doesn't separate into its ions. And then lastly, we have another 3 barium 2+ and 6 Cl-. Okay, so this is our total ionic equation. And now for part B, we need to write out our net ionic equation. So the difference between ionic and the net ionic equation is the net ionic equation does not include any spectator ions. So spectator ions, I'll just write the definition down here. They don't participate in the actual reaction. And they appear on both sides of the reaction equation. So they appear on both reactants, and the product side. So in our case, the spectator ions that appear on both sides would be like this 3 barium 2 plus and also this 6 Cl minus. So we need to list them. So I'm just going to say, for example, barium 2 plus and the Cl minus. So now let's write out our net ionic equation that doesn't include the spectator ions. And you end up getting 2 aluminum 3 plus 6 OH minus produces 2 aluminum hydroxide. Solid. Okay, so now we have our net ionic equation. So now let's see what the junior tutor said. Write the total ionic equation. Write the reactants, aluminum chloride, barium hydroxide. Predict the products. So when we have a double displacement reaction, they showed the products. And then they balanced the equation. And then noted that the aluminum hydroxide will become a precipitate. So they have the total ionic equation, and then they wrote out the net ionic equation, and they didn't specify the spectator ions, but it's kind of assumed because the barium and the chlorine are no longer in the net ionic equation. So this solution is correct. And I'm just also going to add that the spectator ions would therefore be barium 2 plus and Cl minus, just to complete the question. Okay, so question number 5. Aluminum chloride reacts with barium hydroxide in an aqueous solution. So that's pretty much the same reaction as our previous question. So we need to write down this equation again. So when we have aluminum chloride, aluminum has a 3 plus charge and chlorine has a -1 charge. So therefore we need 3 chlorines to neutralize that aluminum. And this reacts with barium hydroxide. So barium has a 2 plus charge, and hydroxide only has a -1 charge. So we need 2 hydroxides to neutralize the barium. And when a double displacement reaction occurs, then we kind of swap our cations and our anions so that they're with the opposite partner. So for aluminum, it'll now be with the hydroxide. And we don't know what state it's going to be in. And we have our second product, which is barium chloride. Again, we don't know the state that they're in. So to find out whether or not these products will be a solid or if it's going to be aqueous, we need to look at the solubility rules. So for example, if you had a compound containing lithium, sodium, potassium, or ammonium, these compounds will always be soluble. So for our case, we have aluminum hydroxide. So if we go down here, we can see that the hydroxide ion is soluble with calcium, strontium, barium, lithium, sodium, potassium, or ammonium, and it's insoluble with any other ion. So in our case, it's with aluminum. So since aluminum's not part of that list, we know that this compound is insoluble, so it will precipitate in the solution. So now let's look at barium chloride. If we look at this chlorine, when you have a compound containing chlorine, bromine, or iodine, this is insoluble with silver, mercury, or lead, and it's soluble with any other ion. So in our case, it is paired with the barium, so this compound is aqueous. Okay, so we know our products now, and to answer the next questions, we just need to first balance the reaction. So we have, notice we have 3 chlorine ions and 2 hydroxide ions on our reactant side, and we have 3 hydroxide ions and 2 chlorine ions on our product side. So to make sure everything is balanced, we just need to put on the opposite subscripts as our coefficients. So for example, we need to put a 2 in front of the aluminum chloride and 3 in front of the barium chloride. And we need to put a 3 in front of the barium hydroxide and a 2 in front of the aluminum hydroxide. So now if we look at all of our compounds, everything should be properly balanced. Okay, so now we can actually start our question. So part A, find the maximum mass of precipitate that will form if 80 milliliters of 0.312 mole per liter aluminum chloride is mixed with 100 mils of 0.315 mole per liter of barium hydroxide. So for this question, it's multi-step, and basically we want to find the maximum mass of precipitate. So the maximum mass of our aluminum hydroxide. So to do this, we need to find out which one of our reactants is the limiting reagent. So for step 1 of answering this question, we need to find the number of moles of both reactants. So recall that number of moles can be equal to concentration times volume. So the number of moles of aluminum chloride is equal to, I'm going to convert my 80 milliliters to liters just so that my liters can cancel out when I multiply by the concentration. So 80 milliliters is the same thing as 0.08 liters, and then we multiply by 0.312 moles per liter. So now we get a number of moles of 0.02496 moles of the aluminum chloride. And now for the number of moles of barium hydroxide, we do the same thing. So let's convert our milliliters to liters. So 100 milliliters is the same thing as 0.1 liters. And its concentration is 0.315 moles per liter. Okay, so if we multiply it out, you get 0.0315 moles. Okay, so when finding limiting reagent, it doesn't necessarily end with which one has the least amount of moles, because we have to take into account the mole ratios in our balanced equation. So this brings us to step 2, which is to find the hypothetical number of moles of our product, which is going to be the aluminum hydroxide. So if we had 0.02496 moles of aluminum chloride, and all of it reacts to form our product, aluminum hydroxide, then we know that we needed 2 moles of aluminum chloride to produce, we produced 2 moles of aluminum hydroxide for every 2 moles of aluminum chloride. So I know this because these are the coefficients of my balanced reaction. So basically, they react 1 to 1, and I'll have the exact same number of moles formed of my precipitate. Okay, so we know how many precipitate would be formed if all of our aluminum chloride reacts. So now let's do the same thing for our barium hydroxide. So the number of moles of barium hydroxide is 0.0315 moles. And if we were to multiply it by its molar ratios, we know that 2 moles of aluminum chloride is formed when 3 moles of barium hydroxide reacts and notice that they react at a 2 to 3 ratio. So if we were to multiply this through, you only get 0.021 moles of barium or aluminum hydroxide that is formed. So now we know that barium is our limiting reagent. And the maximum amount of aluminum hydroxide that can be formed for this reaction would only be this 0.021. Since it'll form this much and then our barium hydroxide is going to run out, so we won't be able to form any more product. So now for step 3, I'm going to start a new page. For step 3, we need to now find the mass of aluminum hydroxide that we are the maximum mass of precipitate that will form. So we're going to use the equation mass is equal to number of moles times the molar mass. So we would first need to find the molar mass of aluminum hydroxide. So the molar mass of aluminum hydroxide is equal to the molar mass of aluminum plus 3 times the molar mass of oxygen plus 3 times the molar mass of hydrogen. So if we look up all these values on the periodic table, the molar mass of aluminum is 26.98 grams per mole. The molar mass of oxygen is around 16 grams per mole, and the molar mass of hydrogen is 1.01 grams per mole. So if we add these all up, we get a molar mass of 78.01 grams per mole. So now we can plug that into our equation to solve for mass. So our mass is equal to the number of moles that was formed when barium runs out. So from the previous step, it was 0.021. And then we just multiply by the number of the molar mass, which is 78.01. And you get a final mass of 1.64 grams. So therefore, 1.64 grams is the maximum mass of precipitate, which is aluminum hydroxide. Okay, so that was only part A of question 5. So now we have to try to solve part B. Calculate the concentration of barium ions in the initial solution of barium hydroxide. So if we write out just the reaction of barium hydroxide that dissociates into its ions, you get barium 2 plus 2 OH minus ions. So if we see here that barium and barium 2 plus, they're at a 1-to-1 ratio. So therefore, the concentration of barium hydroxide would then be equal to the concentration of our barium ions. So in the initial solution of barium hydroxide, so that means we have 0.315 moles per liter of our barium ions. That's just going to be the same value. Okay, so let me go back to the previous page and we can see what the junior tutor said. For part A, find the maximum mass of precipitate that will form. So they wrote out the reactants and predicted the products, and they balanced, and they found out that aluminum hydroxide is the precipitate. So they calculated the number of moles of both for the reactants, and then they took into account the molar ratios to find the moles of aluminum hydroxide that can be produced. So barium hydroxide produces the less, so it is the limiting reactant. So therefore 0.021 moles of aluminum hydroxide will be produced. So when you convert this to the mass, which is on my next page, you get 1.638 grams. Yep. And now calculate the concentration of barium ions. So initially we have 100 mils of 0.315 mole per liter barium hydroxide. And they said that you produce 1 barium ion for every 1 barium hydroxide, so it's just going to be the same concentration. So this solution is correct. Okay, so question number 6. How many nitrogen atoms are there in 0.64 moles of NH3? So if we had 0.64 moles, and we need to find out how many nitrogen atoms, we just need to multiply this by Avogadro's number, which is 6.022 times 10 to the power 23, and the units will be in particles per mole. So if we multiply this out, our moles will cancel out, and we have 3.854 times 10 to the 23 particles of NH3. So, since the ratio of nitrogen atoms to NH3 is equal to 1 to 1, therefore we also have 3.854 times 10 to the power of 23 nitrogen atoms. Okay, so let's say we wanted to calculate how many hydrogen atoms there are in 0.64 moles of NH3. If we wrote out the ratio of hydrogen to NH3, you'll see that the ratio is 3 to 1. So we just need to multiply this value by 3, and you get 1.16 times 10 to the 24 of hydrogen atoms. But the question only was interested in nitrogen, so I'm just going to put this in a box. So now let's see what the junior tutor said. So 1 mole is equal to 6.02 times 10 to the 23 particles. So if we multiply that, you get 3.853 times 10 to the 23. Since there is 1 nitrogen atom for every NH3 particle, that means that there are also 3.853 times 10 to the 23 nitrogen atoms in the sample. Yep, so this solution is correct. Okay, so question number 7. A 121.2 gram sample of champagne is burned with excess oxygen in a bomb calorimeter. The heat capacity of 17.16 kilojoules per Kelvin. Temperature of the calorimeter rises from 20.35 to 43.69 degrees Celsius. What is the delta U of the reaction value for the combustion of this champagne sample in units of kilojoules per gram? Okay, so when we have a bomb calorimeter, this is a closed system. And delta U of the reaction is equal to the heat of the system, or the internal heat, which is what U is. So we can solve for delta U by using the following equation. where delta U of the reaction is equal to Q over M, which is also equal to C times delta T divided by M. So for this question, C is known as the heat capacity. So this was given in the question. It was 17.16 kilojoules per Kelvin. And T is temperature. So delta T is equal to T final minus T initial. So let's just solve that now. So we need to convert both of these to Kelvin in order to plug it into our equation, since our units for heat capacity is kilojoules per Kelvin. So I'm just going to show at this bottom line here. Our final temperature was 43.69 degrees Celsius. And to convert to Kelvin, you just need to add 273.15. And our initial temperature was 20.35. And if we converted this to Kelvin, we again need to add 273.15. So notice that when we convert to Kelvin, you still get the same delta T value because these two values will cancel out. But it's still good practice to convert to Kelvin just so you can show how the units will change. So therefore, our delta T is equal to 23.34, and then I can just say Kelvin. So these are our C and delta T values. So M is equal to mass, and that was also given in the question, 121.2 grams. So now all we have to do is plug these values in. So heat capacity was 17.16 kilojoules per Kelvin. Delta T was 23.34 Kelvin. And our mass is 121.2 grams. So that means the delta U of our reaction is 3.304, and the units are in kilojoules per gram. Okay, so the junior tutor said that in a bomb calorimeter, delta U of reaction is equal to the heat of the system since it is a closed system. So they wrote out their equation, and since the specific heat is in terms of Kelvin, we need to convert all the Celsius units into Kelvin first. So they added 273. Okay, so they just converted it first, but I also showed that the delta T would just be equal to the same thing if you just subtracted the two. But nonetheless, they got the same answer, 3.30 kilojoule per gram. So this solution is correct. Okay, so question number 8. Why cannot cyclopentadiene be purchased directly from a commercial supplier? Okay, this is because cyclopentadiene spontaneously dimerizes to form dicyclopentadiene. And this occurs via the Diels-Alder cycloaddition. So I can show out the general reaction that occurs when cyclopentadiene dimerizes. So if we had two cyclopentadienes, this spontaneously dimerizes. So I'm going to attempt to draw the air configuration of what this looks like. So bear with me because it's always pretty bad drawing these. Okay, so you get kind of like this structure, which is the dicyclopentadiene. And the reason why we can't purchase this cyclopentadiene directly from a commercial supplier is because the purity isn't guaranteed. So cyclopentadiene is normally generated fresh in the lab by thermal decomposition of your dicyclopentadiene. So basically, the commercial supplier will give you just the dicyclopentadiene, and then in the lab, if you wanted to make only just cyclopentadiene, you just need to do thermal decomposition. Since they don't sell the cyclopentadiene directly, just because it spontaneously dimerizes. So the junior tutor said that cyclopentadiene cannot be purchased commercially because at room temperature, they undergo a Diels-Alder reaction, which is the dimerization of cyclopentadiene to form a compound called dicyclopentadiene. Very high temperature storage is required in order to break the dimer compound, which is very costly. That is why commercial suppliers only sell dicyclopentadiene. Yep, so this solution is correct. Okay, so question number 9. In the lab with chromic acid, it is sometimes difficult to control the products from the oxidation of a primary alcohol. Why can an enzyme produce only an aldehyde, while chromic acid can produce more than one product? So the reason for this is because chromic acid is a very strong oxidizing agent. So for example, if we had a primary alcohol, and if you were to react this with chromic acid, it's a very strong oxidizing agent, so one of the intermediates will be your aldehyde. But then it continues on to oxidize it further into a carboxylic acid. On the other hand, if we had just the enzyme, so let's say this underwent enzymatic oxidation, we're able to stop at the aldehyde. So the reason for this is because enzymes are highly specific and can oxidize only to an aldehyde. So this is why they can also be used, well, they are used in our biological systems. So some examples would be like enzymes, dehydrogenase. Okay, so let's see what the junior tutor said. Alcohols can be oxidized into different products such as aldehydes, ketones, and carboxylic acids. The extent of its oxidation depends on the strength of the oxidizing agent. Enzymes can only produce aldehydes due to their controlled nature and specificity. They can only turn a compound into one product depending on their active site and how they process. Chromic acid, on the other hand, is a very strong oxidizing agent. It can oxidize an alcohol into carboxylic acids if excess chromic acid is added. Yep. So this solution is correct. Okay, so question number 10. Predict the charge of the ion formed by each element and write the electron configuration of the ion. So first, let's write down all the different electron configurations of our ground state elements. So for A, we have selenium. And just to make it easier, I'll do them in the shorthand configuration. Okay, so when writing the electron configuration of certain elements, we first need to divide our periodic table into the different orbital sections. So these first two columns in the light blue is the s orbital, and this section in the green is the p orbital. The middle is the d orbital, and these are all the transition metals. And the last two rows, the lactanides and actinides, are the f orbitals. So when we write the electron configuration, starting from hydrogen, you move left to right across the periodic table until you get to your desired element. Typically, you want to write from lowest to highest energy state. So when we write out the electron configuration, we would first write the row number and then the block letter. So let's do the long way of writing the electron configuration just so that we can see an example of how to do that. So starting from hydrogen, we write the row number and then the block letter, which is S. And then in the superscript, this tells us how many electrons are in that orbital. So there are 2 electrons that can fit in an s orbital. And then if we go to the next row, it's going to be 2s and then 2. And then moving across to 2p, it's going to be 2p6. Then moving down to the next row is 3s2 and then 3p6. And when we get to the next row, some people write 4s2 before the 3d, but most of the times, since the 3d orbital is in lower energy than the 4s, we're just going to write that first. So I'm just going to write 3d10. Oh, let me bring it down a bit. 3d10, and then 4s2. And now up to the selenium, we just write 4p and then count out all the electrons until we get to our desired element. So we count 1, 2, 3, 4. Okay, so this is the electron configuration of a ground state selenium ion. And we can write the shorthand configuration as well. So if we look at the noble gas that comes before selenium, it's argon. So we put argon in square brackets, and then we just continue on writing the electron configuration just like normal. So it's argon, and then 3d10, 4s2, and then 4p4. Okay, so this is the electron configuration of a ground state selenium ion, but we also want to predict the charge of the ion formed by each element. So naturally, we just assume all of these elements want a full octet. So assume electrons follow the octet rule. So let's look at our selenium again. So if selenium wants a full octet, it's much easier if it were to gain an extra 2 electrons. So when we have a selenium 2- ion, that means it gained 2 electrons, making its new electron configuration the same as krypton. Okay, so now let's go to the next element. Do it in a different color. So next we have barium. I'm just going to write the shorthand electron configuration for barium. So it is found right here, atomic number 56. So its electron configuration would be xenon and then 6s2. So for barium to have a full octet, the easiest thing for it to do is to remove its last two electrons. So when we remove electrons, we have a plus charge. So in this case, barium 2 plus will most likely occur, and it's just going to have the same electron configuration as xenon. Okay, so on to the next element, strontium. So let's find strontium on the periodic table. So it's found right here, atomic number 38. So its electron configuration is krypton and then 5s2. So this is pretty similar to the barium. It would just rather lose those two electrons to become strontium 2 plus, and its new electron configuration is the same as krypton. Now let's do our last element, which is cesium. So the ground state electron configuration for cesium is found here. So its atomic number is 55. And its electron configuration is xenon 6s1. So again, it's easier for this cesium to just remove its last electron to become cesium plus, and it's just going to have the same electron configuration as xenon. So now let's see what the junior tutor said. The electrons given follows the octet rule. So selenium has 6 valence electrons, so its possible ionic form is selenium 2 minus. So they said that it'll have the same electron configuration with krypton, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. So for barium, its possible ionic form is barium 2 plus, and they wrote out the whole thing. It'll be the same electron configuration with xenon. Strontium has 2 valence electrons. Its possible ionic form is strontium 2 plus. So it'll have the same electron configuration as krypton. Yep. And then cesium has 1 valence electron. So its possible ionic form is cesium plus. So this will have the same electron configuration as xenon. Okay, so this shows that cesium plus and barium 2 plus are isoelectronic, meaning they have the same electronic configuration. So that means they're also isoelectronic with xenon as well. So this solution is correct. Okay, so question 11. The iodine monochloride molecule, ICl, has a bond length of 2.49 angstroms and a dipole moment of 1.21 d. So this is called a debye. Calculate the effective charge on chloride in units of electronic charge. Okay, so to do this, we're going to use the equation for dipole moment. So it's just denoted as this U is equal to QR. So this is our dipole moment. Q is the charge, and R is the distance separating the charge. Okay, so before we plug anything into this equation, I'm just going to convert all the units so that they are all the same. So if we recall that 1d or 1 debye is the same thing as 3.34 times 10 to the negative 30 coulombs times meters, and also 1 angstrom is the same as 10 to the negative 10 meters. So now let's first solve for charge. So to solve for charge, it's going to be the dipole moment divided by R, which is the bond length. So this is equal to 1.21 debye. And then we multiply this by the conversion factor, where 3.34 times 10 to the negative 30 coulombs times meters for 1 debye. And this is all divided by the bond length. So this was 2.49 angstroms. And then again, we would just multiply this to convert to meters. So 10 to the negative 10 meters divided by 1 angstrom. So now we have our final charge in coulombs, and its value is 1.623 times 10 to the negative 20. Okay, so the question asks for the effective charge on chlorine in units of electronic charge. So step 2. For electronic charge, we just need to take our value in coulombs and multiply it by the conversion factor to convert to electronic charge, which is E. So 1E is equal to 1.602 times 10 to the negative 19 coulombs. And you end up with 0.101 E. So this is our effective charge on the chloride. So now let's see what the junior tutor said. Dipole moment is given by U is equal to QR. Q is the charge in coulombs, and R is the distance separating the charge. Rearranging the equation to solve for the charge, they also got 1.623 times 10 to the negative 20. And then they convert it to electronic charge, so they got 0.101. And chlorine is more electronegative than iodine, so they just summarized that the effective charges would be chlorine negative 0.101 and iodine is positive 0.101. So the solution is correct. Okay, so question number 12. Enter the full electron configuration for sulfur 2-. What is the atomic symbol for the noble gas that has this electron configuration? So first, let's write the electron configuration of just a ground state sulfur atom. So to do that, we first need to divide our periodic table into the different orbital sections. So for example, these first two columns is the S block, and these columns in the green is the P block, and the middle transition metals is the D block, and the last two rows, so the lactanides and actinides, is the F block. So when we write down electron configuration, we start from hydrogen and then move left to right down the periodic table, writing the row number and then the block letter. And we do this in order of increasing energy. And in superscripts, we would also show the number of electrons that are in each of those orbitals or suborbitals. So starting from hydrogen, we can start to write out our electron configuration for the sulfur. So sulfur is found here, atomic number 16. So we just need to write 1s2. So this is both hydrogen and helium configurations. And then down to the next row, it's going to be 2s2. And then moving across to the P block, the row number is 2p6. And then to the next row, it's 3s2. And then when we get to our 3p orbital, we just need to count out all the electrons until we get to the sulfur. So it's 1, 2, 3, 4. 3p4. So this is the electron configuration of a ground state sulfur atom. But the question says the full electron configuration for sulfur 2-. So when we have a minus charge, this means we gained electrons. So when we have a 2- charge, that means we gained 2 electrons. So now our new electron configuration starts off the same, but once we get to our 3p orbital, we added an additional 2 electrons, so this becomes 3p6. So if we look at our periodic table, this is the same electron configuration as argon. So then we can say that argon and sulfur 2- are isoelectronic because they have the same electron configuration. So now let's see what the junior tutor said. Sulfur has 16 electrons. Add 2 more to get the -2 charge, so sulfur 2- has 18 electrons. The full electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6. This is isoelectronic with argon, which also has 18 electrons. Okay, so this solution is correct. Okay, so those are all the questions for today's session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. Also, if you enjoyed today's video, you can give it a like and a comment, and don't forget to share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.